YAML, sklearn, model selection, repeated stratified k-fold. Description: repeated stratified k-fold is a cross-validation technique specifically designed for datasets with class imbalance. It extends stratified k-fold by repeating the splitting process multiple times, allowing for more robust evaluation of a model's performance. Inputs: n splits the number of fold splits to be created. N repeats the number of times to repeat the splitting process. Random state controls the random number generator for splitting the data. Outputs: a generator object that yields train test splits. Each split is represented as a tuple of two arrays. Train index indices of data samples belonging to the training set for that split. Test index indices of data samples belonging to the test set for that split. Steps: data splitting: the data is divided into k-folds n splits while ensuring that the proportion of each class is maintained in each fold. Repetition: the entire splitting process is repeated n repeats times, yielding a total of kn repeats splits. Yielding splits: the generator yields each split as a tuple of train and test indices. Metrics: accuracy: a measure of how often the model correctly predicts the class label. Precision: the proportion of correctly predicted positive instances out of all instances predicted as positive. Recall: the proportion of correctly predicted positive instances out of all actual positive instances. F1 score: the harmonic mean of precision and recall, providing a balanced measure of model performance. ROC: AUC area under the receiver operating characteristic curve, indicating the model's ability to distinguish between classes. Visualization plots: confusion matrix: a visual representation of the model's classification performance, showing the number of correctly and incorrectly classified instances for each class. Precision recall curve depicts the trade-off between precision and recall at different classification thresholds. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Fine-tune parameters: n splits experiment with different numbers of folds to find the optimal balance between bias and variance. N repeats increase the number of repetitions to obtain more stable and reliable performance. Estimates: uncertainty methods. Bootstrap resampling: repeat the cross-validation procedure multiple times, sampling data with replacement, and calculate confidence intervals for performance metrics. Bayesian model averaging: combine predictions from multiple models trained on different data. Splits to reduce uncertainty. Challenges and fixes. Challenge 1: high computational cost for large datasets and a high number of repetitions. Sample use case training: a complex deep learning model with millions of samples and 10 repetitions. Fixes: reduce n splits: use a smaller number of folds to reduce the number of training sessions. Reduce n repeats: decrease the number of repetitions while still maintaining sufficient robustness. Optimize hardware: utilize powerful GPUs or cloud computing resources to speed up training. Challenge 2: overfitting to the training data when the number of repetitions is too high. Sample use case training: a linear regression model with 100 repetitions on a small dataset with high variance. Fixes: regularization: add L1 or L2 regularization to the model to prevent overfitting. Early stopping: monitor the performance on a validation set and stop training when the performance starts to decrease. Reduce n repeats: decrease the number of repetitions to reduce the risk of overfitting.